Intro. Exactly that. You know that golden telescope we humans built? It's taking some mind-blowing pictures of space right now. Well, it turns out it's so powerful it might have just shattered our understanding of the universe. It is difficult enough to imagine a time roughly 13.7 billion years ago when the entire universe existed as a singularity. According to the Big Bang Theory, one of the main contenders vying to explain how the universe came to be, all the matter in the cosmos, all of space itself, existed in a form smaller than a subatomic particle. Once you think about that, an even more difficult question arises. What existed just before the Big Bang occurred? For years, researchers have made a series of speculations, but there is no evidence to prove that something is true or false. Now, for the first time, the James Webb Space Telescope has peered into the distant past of the universe, giving us an unexpected discovery. It presents major challenges to our understanding of the cosmos. What was there before the Big Bang, and what is it that the Webb telescope has uncovered that has shocked everyone? All this and more in today's episode of Eyes 200M. The question of what existed before the Big Bang itself predates modern cosmology by at least 1,600 years. 4th-century theologians such as St. Augustine wrestled with the question of what existed before God created the universe. His conclusion was that the biblical phrase in the beginning implied that God had made nothing previously. Moreover, Augustine argued that the world was not made by God at a certain time but that time and the universe had been created simultaneously. In the early 20th century, Albert Einstein came to a very similar conclusion with his theory of general relativity. Just consider the effect of mass on time. A planet's hefty mass warps time, making time run a tiny bit slower for a human on Earth's surface than for a satellite in orbit. The difference is too small to notice, but time even runs more slowly for someone standing next to a large boulder than it does for a person standing alone in a field. Based on Einstein's work, Belgian cosmologist Reverend Georges Lemaitre published a paper in 1927 that proposed the universe started out as a singularity and that the Big Bang led to its expansion. According to Einstein's theory of relativity, time only came into being as that primordial singularity expanded toward its current size and shape. Case closed? Far from it. This is one cosmological quandary that won't stay dead. In the decades following Einstein's death, the advent of quantum physics and a host of new theories resurrected questions about the pre-Big Bang universe. Here's a thought. What if our universe is but the offspring of another, older universe? Some astrophysicists speculate that this inflation theory story is written in the relic radiation left over from the Big Bang, the cosmic microwave background, CMB. Astronomers first observed the CMB in 1965, and it quickly created problems for the Big Bang theory, problems that were subsequently addressed for a while in 1981 with the inflation theory. This theory entails an extremely rapid expansion of the universe in the first few moments of its existence. It also accounts for temperature and density fluctuations in the CMB but dictates that those fluctuations should be uniform. That's not the case. Recent mapping efforts actually suggest that the universe is lopsided, with more fluctuations in some areas than in others. Some cosmologists see this observation as supporting evidence that our universe bubbled off from a parent universe. In the words of California Institute of Technology researcher Adrian Eriksik, in chaotic inflation theory, this concept goes even deeper. An endless progression of inflationary bubbles, each becoming a universe, and each of these birthing even more inflationary bubbles in an immeasurable multiverse. Still, other models revolve around the formation of the pre-Big Bang singularity itself. If you think of black holes as cosmic trash compactors, they stand as prime candidates for all that primordial compression. So, our expanding universe could theoretically be the white hole output from a black hole in another universe. A white hole is a hypothetical body that acts in the opposite manner of a black hole, giving off serious energy and matter rather than sucking it in. Think of it as a cosmic exhaust valve. Some scientists propose that our universe may have been born inside a black hole, and every black hole in our own universe could each contain separate universes as well. But some scientists think the universe started not with a Big Bang but with a Big Bounce. Big Bounce theory. Long ago, medieval religious philosophers in India taught that the universe goes through an endless cycle of creation and destruction in which it evolves from an undifferentiated mass to the complex reality that we see around us, before destroying itself and starting anew. Some contemporary scientists have arrived at an idea with striking parallels. They believe that instead of a Big Bang, the universe expands and contracts in a cycle, bouncing back each time that it shrinks to a certain size. In the Big Bounce theory, each cycle would begin with a small, smooth universe that wouldn't be as tiny as the singularity. It would gradually expand and become clumpier and more warped over time. Eventually, It would reach a point where it would start to collapse and gradually smooth itself out as it shrank to the size of the starting point. Then the cycle would begin anew. For the Big Bounce idea to work, it has to find a way around the singularity theorems developed by British physicists Roger Penrose and Stephen Hawking, which suggest that a contracting universe would shrink all the way down to a singularity in the fashion that a massive dying star eventually condenses to form a black hole. To do that, Big Bounce models depend upon the idea of negative energy counteracting gravity and reversing the collapse so that the universe and time-space would be driven apart again and again. These cycles of contraction and expansion would repeat themselves about once every trillion years. The Big Bounce would make a departure from Western civilization's view of reality since St. Augustine because it would recognize that time actually existed before the universe as we know it. But whether it was a Big Bang or a Big Bounce, the question of what existed before our present universe remains an open question. Perhaps nothing, perhaps another universe or a different version of our own. Perhaps a sea of universes, each with a different set of laws dictating its physical reality. In other words, the cosmos has come a long way, but the most fantastic story of all time isn't fully understood, especially the early chapters. That's why scientists were so excited when James Webb launched. For them, the Webb telescope could be the key. The observatory can look about 3 times as far back in time as the iconic Hubble. The Webb will detect infrared wavelengths long enough to pierce through the dense smog of all the light and dust that sits between Earth and the farthest galactic posts, revealing information about the ancient universe where these wavelengths began their journey through space billions of years ago. All objects, when heated, radiate energy in the form of infrared IR rays. Objects with a higher temperature emit IR rays with higher intensity and longer wavelengths. The first light in the universe was produced by the stars that were born within a few 100 million years after the Big Bang, which supposedly took place over 13.8 billion years ago. The light became fainter and redder until it became invisible to our eyes. JWST is designed to overcome this limitation and allow us to see what was never seen before. The Webb telescope promises a level of perception made possible by its 4 instruments. These instruments can operate at the same time to siphon observations of objects like galaxies, maximizing the efficiency of the telescope. As a result, NASA's James Webb has released stunning images providing new insights into how stars formed in the early universe more than 10 billion years ago. The image shows a young cluster of stars, NGC 346, which is more than 200,000 light-years from Earth, located in the Small Magellanic Cloud, SMC, a dwarf galaxy near the Milky Way. NGC 346 is interesting to astronomers because it resembles the conditions of the early universe when star formation was at its peak. Astronomers believe studying this region could help shed light on how the first stars formed during the cosmic noon, which is only 2 or 3 billion years after the Big Bang. The SMC contains lower concentrations of elements heavier than hydrogen or helium, which astronomers call metals, compared to the Milky Way. Since dust grains in space are composed mostly of metals, scientists expected there would be low amounts of dust and that it would be hard to detect. However, the new data from Webb reveals the opposite. A galaxy during cosmic noon wouldn't have one NGC 346 like the Small Magellanic Cloud does. It would have thousands of star-forming regions like this one, said Margaret Meixner, an astronomer at the University Space Research Association and principal investigator of the research team. But even if NGC 346 is now the one and only massive cluster furiously forming stars in a galaxy, it offers us a great opportunity to probe conditions that were in place at cosmic noon. The NGC 346 houses protostars, clouds of gas and dust in space that are developing into stars. Previous infrared studies of the star cluster have focused on protostars heavier than about 5 to 8 times the mass of our Sun. With Webb, we can probe down to lighter-weight protostars as small as 1/10 of our Sun to see if their formation process is affected by the lower metal content, said Olivia Jones, Science and Technology Facilities Council Webb Fellow at STFC's UK Astronomy Technology Centre. As stars form, they gather gas and dust, which can look like ribbons in Webb imagery from the surrounding molecular cloud. The material collects into an accretion disk that feeds the central protostar. Astronomers have detected gas around protostars within NGC 346, but Webb's near-infrared observations mark the first time they have also detected dust in these disks. Guido De Marchi of the European Space Agency and a co-investigator on the research team said, "We're seeing the building blocks not only of stars but also potentially of planets. Since the Small Magellanic Cloud has a similar environment to galaxies during cosmic noon, it's possible that rocky planets could have formed earlier in the universe than we might have thought." Researchers hope that observing protostars still in the process of forming will reveal whether the star formation process in the SMC is different from what we observe in our own Milky Way. Ms. Jones added, "This is the first time we can detect the full sequence of star formation of both low and high-mass stars in another galaxy. This means we have far more data to study at high resolution, offering us new information on how the birth of stars shapes their environment and even greater insight into the star formation process." That's all the information that we have for you today. Don't forget to give us a thumbs up if you enjoyed today's episode, subscribe if you haven't already, and hit the bell so you never miss out on future episodes. And as always, thanks for watching and we will see you next time.